Hi, my name is John Martin, and today I'd like to talk to you about a new algorithm we developed to identify periodic orbits using the physics-informed neural network gravity model. So in case you haven't gotten the memo, reality is not Keplerian. If you put a spacecraft in orbit, it is extremely unlikely that that spacecraft remains in the same orbit for an extended period of time. And there's a variety of reasons for this. You could have things like N-body effects perturbing your spacecraft, or maybe solar radiation pressure, or maybe the body you're orbiting just has an irregular gravity field. In each of these cases, the spacecraft motion will not typically be periodic. But despite this, we still want periodic solutions. And the tools and algorithms we use to identify these solutions are generally the same, regardless of which of these perturbations we're talking about. So for the sake of discussion, I'm just going to focus our attention on the irregular gravity field case. So when I say an environment has irregular gravity, what do I mean? Well, really every celestial body, be it planets or asteroids, their gravity fields cannot be adequately represented using a point mass approximation. Perhaps most famous of the examples is the fact that Earth is oblate. The equator is a little bit pudgier than the poles, and this will cause your spacecraft motion to precess over time. So to capture those effects, we use things like spherical harmonics. In asteroid settings, spherical harmonics have a few pitfalls, and so you'll see people turn to a polyhedral representation, which, for the same reason, these asteroids cannot be adequately represented using a point mass approximation. So you have this irregular gravity field, and you want a periodic orbit in it. How do you go about finding one? Well, there's two trains of thought. The first is you can go about this problem analytically. Using pen and paper, you can solve things like the Lagrange planetary equations and derive a set of orbital elements that remain fixed over time or fixed on average over time. One of the disadvantages of approaching this problem analytically is the fact that it doesn't really work well when you have a gravity model that is of high fidelity, many terms in a spherical harmonic expansion, or a polyhedral model with hundreds of thousands of facets. So in those cases, you need to turn to numerical solvers, which will work with a high fidelity gravitational potential, but it will typically be slow to compute, and there's not necessarily guarantees on convergence. So I want to talk about each of these in more detail, starting with the analytic method. So this slide is a lot. We're not going to go into great detail, but the point being, if you want to solve the periodic orbit problem analytically, you have to do a lot of mathematical gymnastics. So you might start with a full fidelity gravity model, make some assumptions, and you simplify it. So you just say Earth is really just an oblate spheroid, even though it has many more things or perturbations. You might differentiate that gravitational potential with respect to the orbit elements, throw them into the Lagrange planetary equations, which gives you the time rate of change of the orbit elements. Once you do that, you get these gnarly expressions, and you try and find a solution for which all of these equations are equal to zero. This is a highly nonlinear system, so that's a rather hard problem to solve. So what people will actually do is they'll period average some of these expressions, which gets rid of some of the elements, but leaves you with a few elements that have secular drift. And you can maybe solve for one or two more fixed elements. But what this gives you after all of this math is a frozen orbit at best, not even purely periodic. For reference, a frozen orbit is just an orbit which some of the orbit elements are fixed over time, but not all of them. So, and yeah, just to put salt in the wound, that entire process assumes you simplified your system and you used kind of a crude approximation of the gravitational potential. Imagine going to the full fidelity system. This process grows to be entirely intractable. So that forces us to use these numerical tools. And the way we do that is we frame the periodic orbit problem as a boundary value problem. So specifically, we want our final state after some period to be equal to our initial state, subject to the dynamics of your system. And the way we go about solving this problem is we actually take a Taylor series expansion about the true solution to derive a corrective term. So we might have some initial guess, and we want to slowly shift that initial guess closer and closer to a solution that will yield periodic motion over time. The problem about approaching the periodic orbit problem numerically is that it can be rather expensive. And what I mean by that is, in order to compute this corrective term, you need to integrate, excuse me, the equations of motion. And that requires taking Jacobians and Hessians of those gravitational potentials, which I showed earlier. And that can be very expensive. Even if it's analytical, it will be expensive, but more so if you have to compute these gradients numerically. So just to further emphasize why this is the case, I argue it's because the gravity models we use in these problems aren't very efficient at representing the true system. So a good example is the Earth, where spherical harmonics, it's a wonderful choice if you just want to capture planetary oblateness. But as soon as you want to capture the other perturbations, say mountain regions or subduction zones or hotspots, these very discontinuous gravitational perturbations, and you're trying to represent those discontinuities with a harmonic basis, you have to suddenly superimpose hundreds and thousands of these harmonics together to replicate that discontinuity. So it's a very inefficient basis to represent all of the other important perturbations. Similar things can be said about the polyhedral gravity model, which is trying to represent, smooth surfaces with things that are, tiny triangles, which are discontinuous in their own way. So a question I've been very interested in for my dissertation is, are there more efficient bases for the gravity modeling problem? And if there are, how can they be used for things like periodic orbit discovery? So the short of it is, I think there is a solution. We've been working on it for 2 years, and that's called the physics-informed neural network gravity model. And this gravity model learns basis functions rather than prescribes them. And it finds the most natural set, an efficient set to represent your particular problem. And there are a lot of features about this gravity model that we're really optimistic about, but we don't have time to get into today. So the two features I want to emphasize to you is that the pin gravity model is on the order of 400 times faster than the equivalent polyhedral model, and it's a differentiable gravity model. So when I say that it's differentiable, what do I mean? Well, thanks to a technique called automatic differentiation, which is really just a glorified form of chain rule, we are able to take the exact gradient of any algorithm. So if you have a neural network with inputs that are the Cartesian state that maps to some potential function, using automatic differentiation, we're able to compute the exact gradients, both for Jacobians and Hessians, which can in turn be used in the equations of motion needed for the shooting method. So what's really nice about this is that the gradients are computed exactly and not numerically, which makes this process extremely efficient, and no longer is the shooting method this cumbersome, heavy task. Just to hammer this home, there's a paper you can read more about in our lit review, where they were searching for periodic orbits about the asteroid Cleopatra, and it took 12 days of compute to find 29 solutions. If they were to replace the polyhedral model that they used in their study with the pin gravity model, those 12 days of compute would boil down to 30 minutes on your computer. So talking orders of magnitude faster to find these solutions using the pin gravity model. So we have this powerful gravity model. It seems to be well suited for the shooting method. How does it actually perform? Well, to test that, we pick a random initial condition, which is this gray orbit here. And this doesn't naturally close. And so we apply the shooting method to that initial guess, and we get the red orbit. We repeat the same experiment for 3 different initial conditions, and we get the corrected blue, red, and green orbits respectively. So quantitatively, how do we look at this? Well, in this plot, we're looking at the difference between the final state and the initial state of the initial guesses and of the solutions. So that's represented here on the x-axis. So each orbit corresponds to a different line on this plot, the blue and the blue and the red and the red. And the circle markers correspond to the initial guess, the non-periodic solution, and the stars markers represent the converged solution. Now what you see is that the initial guesses are not periodic on the order of tens of kilometers. But after we apply the shooting method, we're seeing solutions that are maybe 10 kilometers or tens of kilometers off from perfectly periodic. So this is to suggest the shooting method's working. That's great. But the real test of how useful these solutions are is what happens if you propagate these near periodic solutions over time. So instead of a single orbit, what happens when we propagate for 10? Well, suddenly things don't look quite as good. You see that the orbits quickly deviate from the original solution And that's not desirable. Ideally, you want these things to be more convergent than what we see here. So why is this? The shooting method seemed to imply we're approaching periodicity. So why are these long-term propagated orbits so far away from that? Well, it might be because we're looking at this in the wrong space. Sure enough, in Cartesian space, we see orbits that are converging towards periodicity. But if we look in orbit element space, is the orbit elements at the final time step equivalent to the orbit elements at the initial time step? The answer is far less clear. In fact, we see that there are some solutions, the green being the most flagrant example, which does really well in Cartesian periodicity, but quite poorly in orbit element periodicity. So this begs the question, what if we go about solving this problem in orbit element space rather than Cartesian space? So we can do this. We can run the shooting method using orbit elements and apply the corrective term in this orbit element description. But it requires us to compute, again, these Jacobians and Hessians of the gravitational potential with respect to the orbit elements. And this is a really gnarly process to go through analytically. So it's part of the reason people haven't approached the problem in this way before. But what's really convenient here is the pin gravity model can bypass this problem. So we talked about automatic differentiation. What happens if we take our pin gravity model and we augment the algorithm to include the mapping between orbit elements and the Cartesian state? And then we use automatic differentiation to take the derivative of this algorithm to produce the corresponding Jacobian. And then we can repeat this process to get the Hessian. Now suddenly we have exact expressions for the equations of motions using the orbit element shooting method. So let's give it for let's go for a spin. If we try the orbit element shooting method on the same initial conditions, we see that over a single period they seem to find some solutions. But what's really exciting about these solutions is that they are converging in periodicity both in Cartesian space and in orbit element space. So if we end up propagating these orbits on the, for 10 times the initial orbital period, we find that they remain much more stable and consistent with the initial solution than their Cartesian predecessors. The other really convenient thing about formulating a problem in a orbit element space is the fact that if you're a mission designer, you can constrain certain orbital elements and remove them from the optimization process. So let's say you have some mission and you have to have the spacecraft at a certain semi-major axis and inclination about that asteroid. Well, you can prescribe those values and remove them from the optimization and use all of the remaining other orbital elements to enforce that periodicity. And to my knowledge, there was not a way to do this before using Cartesian shooting methods. So this figure just attempts to demonstrate this. We have some scenario with a desired semi-major axis and inclination. We run the Cartesian shooting method, the orbit element shooting method, and then the constrained orbit element shooting method. And the only solution that maintains those desired elements is the constrained orbit element solution. In summary, we have introduced the pin gravity model for use in the periodic orbit discovery problem. We've developed a new orbital element shooting method, which uses the differentiability of this pin gravity model, and we've begun to characterize some of the advantages of this new approach. For future work, we're looking to expand these capabilities to perform the shooting method in a variety of different orbital element spaces. We're also looking to expand the types of shooting methods we use. There's multiple shooting or collocation, other more sophisticated examples, which will help with convergence. And then we want to do a more formal study on the stability of these solutions and characterizing the size of the attracting basins for these different algorithms. So with that, I hope to see you in the in-person presentation, but if not, feel free to reach out via email if you have any questions. Thank you.